But if they don't match, I have to pay attention and do the chain rule. So what is the derivative of something squared with respect to t? 2x, right? 2 times that something. But then chain rule says times the derivative of what was there on the bottom, which is x with respect to t. So this is dx dt. Plus, what about the derivative of this one? 2y times dy dt. So it's kind of like two of the bad scenarios from the previous problem, kind of. Like we have to treat them both like they depend on something else. So we can't turn either one of these into ones. These are just something, whatever they are. Equals 0. And I'm asking us for what? dy dt. So you're going to isolate this right there. You have to isolate that now. So move this entire thing over to the other side. 2y dy dt equals negative 2x dx dt. Right? And then what? Divide by 2y on both sides. And the 2's here will cancel out. So we should get dy dt is equal to negative x dx dt over y. So think about what this is saying. This means x and y are both dependent upon t. Both of them depend on t. We are looking at this as if there's one input, one independent variable, which is t, and both x and y depend on them, on that value. So look, as I'm drawing, right? Drawing the circle, every point I draw is an x and a y. What point I draw depends on the time. So at time 0, here's where I am. But as time starts, I start to draw this circle. And the x and the y depend on what time it is, right? And I come to a stop at some point, right? So if I want to know at this point how fast the y coordinate's changing, I need to know a couple of things. I need to know the point you're talking about, the x and the y coordinate. But I also need to know what? How fast the x is changing there too. Then I can give you the answer. So it's even more information you need in order to solve this, but we can still do it. Another question?
Yeah, if you were just going to solve that mathematically, like once you know the time and the coordinate of x, you can just multiply that and move that x over on top of the time, and that's your ratio.
Say again? If I knew the point, like someone gave me the x and y, I would know those two.
Right, and then if you knew the time.
This would have to be given to us in the problem for us to solve it.
But once you had the time, then you could fill in t and x?
No, because this is a derivative. So remember, derivative is an instantaneous rate of change, right? It's what's happening at an instant in time. And so as soon as you stop time, as soon as you stop it, derivative isn't there anymore. Hang tight. I mean, seriously, we're going to get into this a lot heavier next class, or the next section, because we're going to be doing problems where we have what are called related rates. You've got one thing's moving, something else is moving related to it. We're trying to figure out relationships between them. It's one of the hardest sections in the whole class, word problems. But it's all going to come down to this stuff. Can you do this? And in the problem, one of those will be given. Right? This will be given to us.
In the next section?
In 2.7, yes. All right. So I could have also asked for what in this? I could have said dy dt. I could have said dx dt, which wouldn't have been too bad because we would have had the same derivative. It's just what we would have solved for would have been a little different. We would have moved the other one over.
dt over dx.
What's that?
Could you say like dx over
No, you can't flip. You wouldn't flip it. Don't treat this like a fraction, like in the sense that you can multiply both sides by the reciprocal. Look at it as a derivative. Yes.
I'm still tripping on this dx over dt thing.
Yes.
What if the rate, I mean, granted, if you're drawing a circle, that's one thing, but if you're accelerating, let's say it was based on, how much gas you're getting as per how much mile velocity or something, and it was something that's changing, would you still be able to use the dx dt, or is the dx over dt have to be proportionate with dy dt?
It all depends on how you want to draw the circle, and that's why I need to know some more information, which was not given to us. All right? I started drawing the circle. I could do it nice and uniform like this, or I could do something like this. Oh, sorry, that's supposed to be a circle. Speed up, slow down. I need to know about what's happening, and that I did not provide information for. All I'm trying to get you to see right now, and this is really amazing, is that if you have any equation with any variables in it, you can always find a relationship between their rates of change with each other with respect to time. I'll give you an example of an equation that may look familiar to you. I'm going out a little bit on a limb here because I wasn't planning on talking about this. But I know a lot of you have seen this before, maybe not exactly written like that. And I may be using the wrong R, maybe you use an uppercase R, I don't know. What is that? Pressure times volume equals moles times Avogadro's number times temperature, something like that, right? But in this equation, these things are usually constants. And this is basically telling you that the pressure times volume equals temperature. Pressure times volume equals temperature. So the way it works is like a balance. If your pressure drops, this side gets smaller, right? And that means this side must get smaller. So that's why when you take a soda can and you open it, right? You've just dropped the pressure. The air that comes out of that is cold, colder than it was before you released the pressure. Yes? This is how an air conditioner works.
That's why there's like a small histogram whenever you open a soda can.
Yeah. You know your air conditioner, we turn your car air conditioner on, and you hear that thing click in, you hear it click in, yes? It's taking Freon, it's pressurizing it, and then it's spraying it through this very tiny little orifice, and on the other side of that orifice is low pressure. So it's high pressure on one side, low pressure on the other. As it passes through, this law says lower pressure means lower temperature. So the Freon on the other side is really cold because it's low pressure now. And then that's what runs through coils, and then your fan blows over it, and that's the cold air. And then it goes back through the cycle, and it gets repressurized, and it just continues. So you're getting free cold air, right? No, you have to pressurize it, and that pressurizing it requires energy, so it's not free, right? But Freon's amazing because you can just continually run it through that cycle. It'll just continue to cool and cool and cool and cool. As long as you can run the compressor to pressurize it, you've got cold air. All right, what the hell am I talking about here? Okay, pressure, volume, moles of gas, whatever, temperature, right? So let's say I have a scenario where I have this relationship and I've got time. So I've got some experiment running, I've got time going, and there's things happening within the experiment. And this is the law it's following, right? I can ask right now, hey, at a specific point in time, what was dV/dt? What was the instantaneous change in volume with respect to time at that specific point in time? I can ask that question now.
Yeah.
And here's what it would be. I would need to take the derivative with respect to time on both sides of this equation. Now keep in mind, little t is not capital T. Capital T is temperature. So if I took the derivative with respect to time of this, I said I'm going off on a tangent here, but trust me, we are going to do this in 2.7. So don't look at it as like, well, he's just talking gibberish up here. This is, we're headed here, okay? But look at this. There are only two constants in the problem. There they are. Everything else is a variable. The pressure depends on time, the volume depends on time, the temperature depends on time, right? So when I take the derivative of the left side, that's a product rule. Product. What's the derivative of a product? Well, it's the derivative of the first one times the second one plus the derivative of the second one times the first one equals. The right side, this is all a constant, right? You don't need the product rule because this is all a constant. It's just going to come for the ride, isn't it? So I'm going to put nRT, or nR, times the derivative with respect to t of capital T. And now, what is the derivative of p with respect to t? Shit, I don't know. dp dt, whatever that is. I don't know what it is. Times v plus derivative of v with respect to t. dv dt, which is, I don't know, times p, right? Equals, over here, n times r times what? D capital T over d little t, right? I have created the relationship between how things change for this gas law. So what did I say I wanted to know? If I want to know dv dt, right? If I want to know that, here it is. Good, it appeared here, right? I can solve for that. I can tell you how fast the pressure is changing with respect to time. I can tell you that, but here's what I need from you. I need you to tell me what the volume was at that moment in time, the pressure at that moment in time, not the temperature, right? No, temperature didn't matter. But I need to know how fast the temperature was changing, and I need to know how fast the pressure was changing. So if you can measure those things for me during the experiment, how fast the pressure changes, what the volume was, what the pressure was, and how fast the temperature was changing, I will be able to provide you with the change in the volume at that point in time. And I'll have to move things around and stuff, but I could do it. Make sense? What's beautiful about this works for any equation. Doesn't matter where you are, physics, chemistry, biology, finance, any variables connected together, you can find their relationship in terms of the rates at which each other affect, I'm not saying that right, the rates at which they change, how that affects one another, you can do that for any equation. This is very powerful. Yes?
What happens when, I guess I'm going to go back to the limit on this one, I guess when one of these variables approaches infinity? Does I get necessarily really big as well?
Well, that you don't need the derivative for, because if t goes to infinity, so does this. Right? So think about it this way. Let's say you have a container. You have a temperature, pressure, volume, right? You have a container, so your volume is fixed. Let's say your volume is fixed. Your temperature starts to go up. What happens? This side's got to go up too. And since the volume is fixed, that means your pressure goes up, right? So that question can be answered without the calculus. I think what you're asking is, what if the rate of change in temperature goes to infinity? You can figure that out. You just have to set it up in here. Just figure out where it is and how it relates to the other variables. I don't know. This is too much of a too complicated for me to answer something like that. I think an easier example, you would see how we could make those relationships. Yes?
Would it be wrong for me to change the d to a triangle at any point in time?
It would be wrong because the delta is change, but it's not infinitesimal change. We understand this as being change, but calculus, we use the differential d to let you know we're taking a limit. We're letting this change go to 0. If you just write delta, it's assumed to pretty much be greater than 0, and it's not a limiting change. We're not letting it shrink down. Remember, because when we did a secant line, right, we had to move that point on top of that one, and to do that, we had to let the changes go to 0. This tells you you're doing that. Now, I've seen people use it in calculus, the delta, but the differential is really the implication of the limit being applied.
Because in chemistry, it's a triangle, let it be. So it's weird.
Are they doing derivatives? See, yeah, that's the thing. They're not doing derivatives. They're just showing you change in this, change in that. They're not talking about instantaneous rates of change. They're talking about average rates of change. You're looking at an average between two clear points in time in chemistry, right? Which is average.
Sometimes. So we do both.
Well, if you're doing it at an instant, then it's a derivative, unless you have something that measures it at that instant, right? But that's like looking down at your speedometer. It's telling you your speed at an instant in time, right? But that's, yeah, okay. Okay. Let's get back to ground. I think we need to see some of this ugliness that can happen. Let's look at this one. I'll tell you all this story. I don't know why I tell this story. Why do I tell this story? I don't know. People seem to remember, when I tell this story, they seem to remember this whole thing better. So when I was in graduate school, for any of you that are going to go do graduate school, most of you are STEM majors, so if you go to graduate school, you'll know what it's like to actually like suffer through living through school, like living it, breathing it, eating it, everything. I used to sleep in literally on a bench in an office, and I'd just sleep there for 3 days. My parents would come check on me and bring me food and make sure I'm alive, and they hadn't heard from me for 3 weeks. And so I was very into the mathematics. That's all I did. So I didn't have a whole lot of time for much of anything. But you have to have some balance in your life, right? So what I would do is once every 2 or 3 weeks, I'd go out to this club, and I should probably not record this. I'll just It all depends on with respect to what variable, right? When you're talking derivatives now, we have now taken you out of this fishbowl of like derivative of x is 1, derivative of x squared is 2x. This is a bigger picture here now. There's more involved. For the majority of your test, it's going to be the normal stuff. But once we get to this implicit stuff, you have to think bigger, all right? You have to pay attention. So this y prime, for us in this class, this y prime will always mean dy dx, unless I tell you otherwise, which I won't. Okay, so if I give you that, you can assume it's with respect to x. I miss those days. Good stuff. I do. When my graduate advisor was like, we were talking the last day I ever had class with him, and we were up on the roof of the building. We were talking. We were talking about joy and just happiness, and he was like, he's like, doing mathematics is the second most enjoyable thing that he had ever done. And I was like, well, what's the first? And he's like, my daughter being born. And I was like, wow, he put that in front of his marriage. Wow, that's pretty impressive. So I don't know. I mean, like people who do math, like I know we have one potential math person. Like it just, you have to love it. It has to be the joy. You know, you get that joy when you get a problem right. Like the higher you go in math, the fewer times that happens. Okay, but the more rewarding it is. You know, like to work on a problem for like 4 or 5 weeks and get it. You know, that's like. It's just I don't know, can't reproduce it. It's not for everyone though. Or not get it, yeah.
Like that one time with your professor, typo.
Oh yeah. All right, so you've all done this problem by now, because I've been chatting here. What are y'all thinking here?
With respect to...
I said with respect to x. I heard quotient rule. We could do that? Okay, let's try it. That's what I heard, so we'll do it. I'm going to take derivative on both sides with respect to x. And on the right side with respect to x. Now look, the derivative of a constant is always 0. See, there's never a trick. That's never a trick question. That's never like, oh, with respect to what variable. No. A constant does not have an instantaneous rate of change. It's always 0. Well, it does, but it's 0. So what are we doing on the left? Quotient rule? Derivative of top times the bottom, minus derivative of bottom times top, bottom squared, all that. So the derivative of the top times the bottom minus the derivative of the bottom times the top all over y squared. And notice my derivatives with respect to x. Equals 0. All right, what is the top left right there?
Y.
That's 1, right? That's just a 1. Derivative of x with respect to x, that's 1. What is this one right here? dy dx. And that's good because that's what I'm trying to find, right? So the fact that it appears there is a good thing. So I have 1 times y, which is y, minus dy dx times x over y squared equals 0. And a fraction can only be 0 when? Only if the numerator is 0. Please remember that. Oh, I thought we talked about this. A fraction can only be 0 if the top is 0. Because you can always multiply both sides by b. And so it just turns out to be a is 0. So you get, yes, and we're saying y can't be 0. Yeah.
So we split these up, right? So we can put y over y squared minus dy over dx times x.
Oh yeah, you could have done that also, but I'm just clearing out the fraction right away. I'm just multiplying both sides of the equation by y squared. It's gone. And then just move things around. I think I'll move this piece to the other side so it'll become positive. And finally, divide by what? x.
Well, we did all that just to flip it.
Yeah, we did all that to flip it. Was there a question? I multiply both sides by y squared. Because this is a big fraction, I just multiply y squared here, and it cancels. And then over there, 0 times y squared is 0. Right? Hey, but wait a minute. If x over y is 1, doesn't that mean that if I flip them, it's still 1? Right? Like 4 over 4 is 1, but flip it, 4 over 4 is 1. Like, these are the same, right? If it's 1, these are the same. So if I flip that, I should still have 1. So this answer should be what? 1. Does that seem weird? Does that seem weird that this would be 1?
Not really.
No?
Because if you think about it, if you have like a...
Wait, is this your way of telling us anything like what we do to dy dx?
Yeah, there's a moral to this story. Look, check this out. Forget implicit differentiation for a second. Start the problem over. Multiply both sides by y. That's an explicit equation. Y is solved for x, isn't it? Right? This is like y is equal to x. And if I were to come in here today and I said, hey, what's y prime, everyone? Everyone would have said, derivative of x would have been 1, right? The answer should be 1. What I'm getting at is this. You can do implicit differentiation on this and get an answer. That answer may look like this, but it may simplify to be this, right? And if you go back and look at it, you say, oh crap, I could have done this without implicit differentiation and just done my normal derivative like I did before I walked in today and got the answer faster. So you just pay attention to what you're doing, you know. You don't want to work hard if you don't have to.
It's good to know that you will still get back.
That's right, you should. There are a couple of pretty challenging problems late in the section, and I worked on a few of them. I did all the homework on the video. I got a little bit rushed at the end because they needed the room, and I had to really rush through the last one. So I'll see how you do with that. Here's our plan. We have next class a quiz that's going to take place in the beginning, right? 15, 20 minutes. Power rule, product rule, quotient rule, chain rule. I think I might give you kind of an easier implicit, just kind of like the x squared plus y squared is 16 type thing, just to make sure you're doing the right sorts of computations, or you know the right things are turning into 1, the right things are not turning into 1. And then after that, we have really slated for us another day of implicit differentiation. So I would like to get into some heavier problems with the implicit next class, and then maybe take a sneak peek into 2.7. I'm not saying you don't need to watch the 2.7 video, but if you'd like to, you can, because it's a long video. 2.7, I think it's like half an hour, and there's a lot in it. So
It's going to be on this and the previous section?
everything from power rule, which is like n comes down, x to the n minus 1, which is 2.3.
The chain this, right?
Yep. Power, product, quotient, chain, this.
What's our next test?
That's a great question. Next test is scheduled for
October 11th.
the 11th. So not next week. Not next week, the week after, and it's on a Tuesday. Yep. Have a good day, I guess. We'll wrap it up. I hate ending early, but we'll wrap it up. Do your homework.